Hello and welcome all. Today we'll be discussing a new chapter in song, which is a very important chapter from any exam point of view. Especially with reference to gate, we'll be discussing this topic and we'll be relating this topic to the previous topics of simple stresses and strains. Okay. Now this chapter, which is also known as principal stresses and strains, is also sometimes known as study of combined stresses. Study of combined stresses. Now what do you mean by study of combined stresses? We'll come to this topic afterwards. First we'll be discussing what is basically the need in song for principal stresses and strains, even though we have already studied simple stresses and strains, right? Before moving on to this topic, I'll be asking you a question. It's a basic question, and if you answer that basic question, we'll be moving on with the relevance of that question to this particular topic, right? Now my question is, we have already studied the chapter on simple stresses and strains, and I have already told you that whenever an equal and opposite force, suppose say a normal force in the form of a tensile load is given over here. Say this is equal and opposite force. This is known as a normal load, right? And we have already discussed the difference between load and force, right? Now this is a body, we have applied normal load upon it. Now my question is, whenever pure tensile load is acting on this body, what will be the normal stress induced in this particular bar? Suppose this is a bar. What will be the normal stress induced in this bar whenever a load of equal and opposite force, say P, is acting on this particular section? I also want to know what will be the shear stress induced in the bar when this normal load is acted on this bar. I also want to know what will be the normal stress acting on the cross section. We have already discussed what is a cross section. Whenever a load is acting and a section is perpendicular to that load, we usually say that section as cross section. But cross section is usually defined in song as the section which is perpendicular to the force acting in the longitudinal direction. Whenever a force is acting in the longitudinal or axial direction and there is a section perpendicular to the direction of that load, it is known as cross section. We have already discussed that, right? Okay. I'll also be knowing from you that what will be the shear stress induced on the cross section whenever a pure tensile load is acting on a bar. Now, whenever we are asking this question, students get confused between these two parts, cross section and bar, right? We have already discussed this particular part, that whenever a pure tensile load is acting, what will be the stress on this particular section? Because in simple stresses and strains, we use simple formula P by A, which deals with simple stresses and strains acting on that A. What is that A in simple stresses and strains? In the stress formula, that is nothing but cross section. And what is that P? The P is the load acting in the direction perpendicular to the cross section, that is also known as longitudinal direction. It may be a compressing load depending on the type of load or the direction in which you are inducing the load. Now, cross section, I just want to know that will this stress be equal to 0 or not? And I also want to know, will this stress be equal to 0 or not whenever a pure tensile load is active? See, Normal stress always comes from normal load. Now this is normal stress, so normal load upon cross-sectional area. We have already studied this. But if we want to calculate shear stress on cross-section, do we know the shear load over here? No. This load is not a shear load. Why? Because the area which we are considering on a regular basis, that is the cross-section, this load is only and only perpendicular to that section. It is not parallel or along that section. If this load would have been parallel to the section or along the section, then we would have told that this load is acting as a shear load. But in this case, cross-section is perpendicular to this load. So this load is acting as a normal load and not as a shear load. So in this case, if there is no shear load, how can be a shear stress induced on the cross section? Am I right? Did you get it? Fine. Moving on. When we are dealing with the bar, it is very important to understand that in the bar there are infinite points present. And whenever a load is acting on a body in song, then there occurs certain deformation in the body, right? Now whenever the deformation occurs in the body, there are many points. Every point will face or will get induced by some value of stress depending on the resistance they pose to the external load, right? Okay. Now the resistance posed by each and every particle may or may not be same depending on the situations or conditions of the load. Now, whenever a particle resists a particular external load, stress will be induced in that particle, and we want to know that particular particle in which maximum stress is being induced. So, we want to know that particular point from all the infinite points in this body where maximum stress is being induced. We are not worried about each and every particle. We are just worried about that particular particle or about that particular plane on which maximum stress is present. Because from the design perspective, being a mechanical engineer, I can say that whenever maximum stress is being acted upon a particular plane or point, that is of utmost importance for me. Because if I save my particular body from that stress, then I can save the entire body from that particular stress. So, the need of the hour is we should be focusing upon that stress which is maximum in the bar. Now, stress is of two types, we already know. One is the normal stress, which may be of any nature, be it tensile or be it compressive, and the other type of stress being shear, right? Now these two have different natures, understood? So these can never be added or subtracted directly. For adding and subtracting these, we have to use certain theories known as theories of failure, understood? Now, in the entire bar, we need to find that point which is having maximum stress. So, till this point, we cannot say that the normal stress in this body is zero. Well, it cannot be also. Why? Because in this bar, one place is there which is known as cross section, and we have already observed that there is normal stress present on the cross section. Hence, this cross section being a part of the bar cannot make the normal stress to be zero. Now, shear stress on the cross section is zero. We have already known by the type of load. Because the type of load is not shear, so we have just put it equal to zero. But after some time, you will be able to achieve to a situation where where you will come to know that on cross section, the thing which we have written over here is correct, right? Now, in the bar, there are infinite number of planes, there are infinite number of points. Hence, we are not going to make a conclusion over here that in the entire bar, like cross section, this will be 0. Hence, this is not 0 until now. Now, we have already seen that when we will be discussing about bar, we won't be considering only cross section. We will be considering that every section passing through that particular point which is having maximum stress induced in it. But initially, you have to know the address. You have to know the particular position. You have to know that point which is having maximum stress induced in it. And this particular point is known as critical point. If it is a particular plane, then that plane will be known as critical plane. So now here we are concerned with only one thing. Where is that particular point, or where is that particular plane in which maximum stress is induced? Now, moving on. Here comes the concept of, now this particular problem will be solved by the concept of oblique plane. Because until now we have discussed in simple stresses and strain only about cross section. Now we will be discussing about oblique plane. Now what is an oblique plane? Now oblique plane can be any plane at any angle or orientation from the cross sectional plane. Now to discuss this thing in detail, we'll be moving on to a new topic, that is the concept of oblique plane, which will give us a clear idea that which plane is having maximum normal stress in the entire bar, which plane is having maximum shear stress in the entire bar, right? Fine. Now, we have already discussed that to discuss the concept of principal stresses, that is the maximum normal or the minimum normal stresses induced in a body, we will be considering all sorts of planes which will be passing through that critical point or the critical plane itself. Now, we know that from a critical point, say A is a critical point on this particular bar, where we have already known that maximum stress is acting, but we don't know the exact location of that particular plane on which this stress is maximum or minimum. The stress may be of any type. The stress may be of shear in nature, the stress may be normal in nature. Now, as we know, we have applied a pure tensile load, and we know that this is acting on this particular cross section. Say cross section is given by the breadth AB, and the thickness of the bar is said to be unity. So, the area of cross section, say A, is equal to AB into AB, the breadth, and thickness is unity. Now we already know the cross section. This is a cross section and this is the load, and hence this cross section is observed in the side view, right? Now this area of cross section is AB into 1, right? Now moving on, AB dash, what is AB dash? Let's see from the triangle over here. AB dash is nothing but, let's say to calculate AB dash, we would say to calculate u cos theta. Now cos theta from this particular triangle is base. What is base of the triangle? It's AB. And what is hypotenuse of the triangle? It's AB dash. We already know AB, right? AB is nothing but the area of cross section because the thickness is unity, right? Now from AB we will be calculating AB dash. Now AB dash is nothing but AB divided by cos theta. Now this is the relation we have achieved. By this relation we would calculate the new area of oblique plane. Now this is nothing but area of oblique plane. Now area of oblique plane is nothing but the original area A, because AB represents nothing but area and the thickness is unity, so it's A upon cos theta. So this is the particular formula we are searching for. Now Any oblique plane can be represented by this area when we already know the area of cross section, which we know. Now, a by cos theta, theta can be any angle, it can be at any orientation. Till now, we don't know this particular value of theta where the stresses will be maximum or minimum. But now, we are moving on to that particular consequence. Let's wait and watch. Now, first of all, we have taken out this relation. Now, by the resolution of vectors, we will resolve this force into two components. One force will be normal to this particular oblique plane. Let's find out what is that load. See, by the resolution of vectors and from the geometry, we know this theta is present over here also. So, what will be the value of the normal force which is acting on this oblique plane? It is equal to P cos theta, right? Now, let me say what is Pn. Pn is normal force to the oblique plane. Pn is normal force to the oblique plane, right? Okay, now let's find out another component of this particular P which is downwards over here. Say this one. Now this is nothing but PS. Now what is PS? PS is nothing but shear force to the oblique plane. It is shear force to the oblique plane, right? Did you get that? Now, we have already resolved P into two components. One is along the oblique plane and one is perpendicular to the oblique plane. Now, what is the value of along the oblique plane? It's nothing but P sine theta. Okay, now, after resolving this, now we are ready to calculate the value of normal stress which is acting at a plane, oblique plane, which is at an angle theta with the cross section. Because we already know we have denoted this as normal stress, but for any oblique plane at angle theta with the area of cross section, you should be writing this as a subscript, okay, to avoid any confusion. Now, this is equal to the normal load acting. The normal load is given by Pn over here, and the area of oblique plane is given by A dash, which I have already mentioned. Now, Pn has already been calculated as P cos theta divided by A dash has already been calculated. It is nothing but A divided by cos theta. So what is the consequence? It's nothing but P by A cos square theta. Now, from here we see that sigma n at any angle theta of oblique plane is given by P by A. Now, what is this P by A? We already know P by A is nothing but the stress acting on the cross section. Okay, so it will be denoted just by single sigma, and we'll be writing this as it is. So this is the relation. This is the normal stress which is acting at any oblique plane at an angle theta with the area of cross section. Right? Now, we'll be deriving another relation. Hope you. Now, after calculating normal stress at this particular oblique plane, we are ready to calculate shear stress, if any. We are not hopeful till now, but let's see by the mathematics what it comes. It's shear stress at an angle theta. It is equal to shear load. Is there any shear load on oblique plane? My goodness. This particular load, which was acting perpendicular to this particular section, also known as cross section, has two components, and one of the components is lying along this, and this particular component which is lying along the oblique plane gives rise to a stress known as shear stress, because it is a shear load. Now let's write it as shear load PS divided by that particular area of the section on which this is acting, and that is the area of oblique plane. Now, it is given by, what is PS? See, PS we have already calculated as P sine theta divided by, what is A dash? It is nothing but A divided by cos theta, which gives rise to Ts at any angle theta, gives rise to sigma. We have already discussed P by A as sigma. Now without wasting time, we will be moving at a rapid speed. Till now we were discussing at a slow speed. We will be increasing our speed and writing this as sine theta into cos theta. Now, we know from mathematics there is a formula known as, from maths we know, trigonometry. We already know from trigonometry that sine 2 theta is equal to 2 sine theta cos theta. So we'll be making a change in our equation so that we can deal with this particular small term known as sine 2 theta. And by this, we'll be moving on to a condition known as shear stress induced at any section which is at angle theta is equal to sigma into sine 2 theta divided by 2. Now this is also a very important equation. Now the two equations we have already got, and from here one thing is crystal clear, that there will be shear stress induced in the bar, right? It may not be induced at all the sections, but it may be induced at some of the sections, and we need to find out that particular section, or we are interested in that particular section which will give us maximum or minimum shear stress. And let's see what will be its value. Now, after discussing these two particular parts, we are ready to find maximum and minimum condition, and we will be getting this help from the trigonometry, right? Now, we have already found the value of normal stress at any section theta from the cross section and the value of shear stress on that particular section. But till now, we don't know what is that plane, or what is the address, or what is the orientation of that plane from the cross section in which maximum stress or minimum stress is being induced, because we are mainly focusing on that particular planes. And the value of stresses on that planes, the value of normal stresses, as known as principal stresses, right? So principal word is mainly used for maximum or minimum. For what? It is used for maximum or minimum normal stresses. See, principal word is only used for normal over here. It cannot be used for shear, so we have written shear stresses separately, right? Now, see, we already know that this value of sigma is already fixed, because the value of load is fixed, the value of cross section is fixed. So, we will be focusing totally upon this particular part. Hence, for maximum value of sigma n, for maximum value of sigma n, you can do two things. Either you can approach by differentiation, or for maximizing or minimizing, taking first differentiation and putting it equal to 0 and finding the critical points, or you can proceed by simple mathematics of trigonometry. Now, moving by trigonometric method, what we see, for maximum value of sigma n, what we see, cos square theta is equal to 1. This is the maximum value of, because we know the maximum value of cos theta can be 1. So the maximum value of cos square theta can also be 1. Now, for minimum value of normal stress at any section theta, we know that the minimum value of any square term we need to take care of here. It is not minus 1, It is a square term, so the minimum value can be equal to 0 only. Understood? Very, very important. Very, very important. Now, we have seen cos square theta can be 1. Now, for this to happen, cos theta is equal to 1. Right? Cos square theta is equal to either 1 plus 1. Let's write it by different color. Either it can be plus 1 or it can be minus 1. Wait. Either plus 1 or minus 1. Now, from this particular part, we'll find the orientation of theta. Now, what is the value of theta for plus 1 or minus 1? We already know it's a cosine curve. So, cosine curve at 0 degree gives you 1, and at 180 degree also it gives you 1. Is it considerable? Either at 0 degree you'll get 1, or at 180 degree you'll get 10. Now what we observe, a 0 degree plane, or say if this tilts by 180 degree, complete half rotation, then it is a same plane. It is a same plane. So you don't need to worry about the two different planes. It's actually a same plane but with different orientations, right? Now, for cos square theta to be 0, for minimum value, cos theta should have been 0. And for cos theta to be 0, we know what will be the value of theta. It's 90 degree or 270 degree. See, these two are again same thing, they are same plane. So basically, we have got one plane where the value of normal stress at that section is minimum, and we have got another plane where the value of sigma m for at any angle theta of the oblique plane, it is maximum, right? So now we have concluded that our maximum value of principal stress will occur on a plane which is coinciding with the cross section, that is the cross section itself, and the minimum value of normal stress will occur at a plane which is at 90 degree, right? So basically this is called plane of minimum normal stress. Plane of minimum normal stress. And what is this plane called as? It is known as plane of maximum normal stress. Now see, we have already known the conditions of the planes at which maximum normal stress and minimum normal stress occurs, right? Now we'll be substituting this theta values in that particular equation of general oblique plane. Now after substituting these values, what we find is that sigma normal max is equal to, substituting the value of theta over here, we find that it is equal to, what is the value of cos theta? It's 1, so it is equal to sigma itself. And what is the value of sigma and minimum? It is theta when 90 joules of student will be equal to 0, right? Now this is the value of maximum and minimum in this particular loading conditions. Now just see that in these loading conditions, what we observe, the load is acting only in one direction, that is, this is a uniaxial loading condition. But in biaxial loading conditions, the case will be pretty different. We need to resolve forces in both x and y directions, right? X and y directions why I am telling, because in biaxial state of stress conditions, we will apply the load in x and y direction, and hence we will resolve it separately to find the value of shear stresses maximum or minimum and value of principal stresses in the entire bar, right? Now Moving on to another section, we are here to find out the value of shear stress at a plane which is at an angle of theta with the cross section. Right? Now, from mathematical point of view, that is trigonometric point of view, you can also find the maximum and minimum values I told you by differentiation method. Right? So, for tau s maximum, the condition is that sine 2 theta should be equal to 1. Now sine 2 theta can be 1 at only one condition, when 2 theta is equal to 90 degree. And theta can be 90 degree only and only when this is 45 degree. Right? Now for tau s to be minimum, we know that sine 2 theta, see, it's not a square term over here, right? So if it is not a square term, we already know that sine of an angle can have a minimum value of -1, right? So what we'll do, the sine 2 theta is equal to -1. So what is the value of 2 theta for it to be -1? It is nothing but 270 degree, right? We know from the sine graph. So 2 theta should be equal to 270 degree, which implies that theta is equals to 135 degrees. So we have got the address of the planes at which the value of shear stresses can be minimum or maximum. This is the maximum, this is the plane of maximum shear stress, and this is the plane of minimum tau s, right? After knowing the address or locations of the oblique planes at which the shear stresses is maximum or minimum, we are ready to find the values of the maximum and minimum shear stresses, right? Now, to know the values of maximum and minimum shear stresses, we will be substituting this value of theta in this particular equations, right? At theta is equals to 45 degree, tau s theta is equal to sigma by 2. Right? Because 45 degree over here gives sine 2 theta is 1, and at theta is equals to 135 degree, tau s theta is equals to minus sigma by 2. Right? So this is the value of maximum and minimum shear stresses. Now what do we observe over here? Our observation is that the shear stresses are complementary to each other. We find that the shear stresses are complementary to each other. Right? Complementary to each other means they are having equal and opposite directions. They are having equal values and the direction is just opposite. Right? So, we have come at a conclusion that on these particular planes, the value of normal stresses will be maximum and minimum. On these particular planes, the value of shear stresses will be maximum and minimum, even though only and only pure tensile load is acting on this bar. This is a uniaxial loading condition. We'll be moving on to biaxial loading condition, but before that, one very important point. We haven't discussed about the value of shear stress on the planes on which this stress is maximum or minimum. We haven't discussed the value of normal stress on these planes where shear stress is maximum or minimum. So, now we need to find out the value of normal stress at these planes and the value of shear stresses at these planes. Now, substituting the value of theta in the particular equation of tau s. Now, at theta is equals to 0 degree, tau s is equals to sine of 2 into 0 is 0 and sine 0 is 0. So it is 0, right? Now at theta is equals to 90 degree. What do we observe? 2 into 90 is 180 and sine 180 is again 0. It means the value of, the value of tau s is 0 on either maximum or minimum value of normal stress. Understood? That is principal plane. So we come at a conclusion that the value of shear stresses, the value of shear stresses on principal planes is 0. The value of shear stresses on principal planes is 0. Right. Now, one more thing is left. What will be the value of normal stresses on these particular planes? So, let's find out the value of normal stresses on these particular planes. So, I'll be rubbing this portion. Now, I am interested in finding the value of normal stress on these particular planes. So, moving on. Sigma n, what will be the value of sigma n at theta is equals to 45 degree plane? Let's substitute the value of 45 degree over here. After substituting the value of 45 degree in this particular equation, what do we observe? We observe that it is equal to sigma into cos square 45. Cos 45 is sigma into cos square 45 degree. Hope you understood this. Now, substituting the value, what do you get? You'll get this value as sigma by 2, because we are already knowing cos 45 is 1 by root 2 and the square of which is 1 by 2. Hence, it's sigma by 2. Now, knowing the value of sigma n at theta is equals to 135 degrees. Now, what will be the value? Now, see, when you substitute 135 degree in this particular equation, cos 135 is nothing but it's, say the value is again 1 by root 2, but it is in the minus form, right? Because it's in the third quadrant. So, second quadrant. In second quadrant, cos is negative, but the square term will make minus 1 by root 2 as positive, right? So it is nothing but sigma cos square 135 degree and it is minus 1 by root 2 square, which is again sigma by 2. Now we come to a conclusion. Now what is the conclusion? The conclusion from here is that the value of normal stress, on maximum or minimum shear stress plane is not 0 under is it visible? Okay, fine. Under uniaxial loading conditions. Because till now we have already derived at uniaxial loading conclusions. When we will do biaxial, let's see, does the result vary from this or not? This may be 0 or not on the maximum shear stress or minimum shear stress planes. Till now, the value is not 0. Till now, whatever we have observed, we have reached at a conclusion, and it will always be valid whenever uniaxial loading conditions are there. Right? Now, these stresses are known as principal stresses, and these stresses are known as the value of shear stresses on maximum and minimum shear stress planes, right? And we have interchanged also. We have found the value of shear stresses on the principal planes. We have also found the value of normal stresses on the planes of maximum and minimum shear. So for now, we'll stop the topic and we'll continue with biaxial loading conditions and studying the values of principal stresses and maximum and minimum stresses on oblique plane. For now, bye. Thank you and take care. Well, thank you.